union ground, also known as a common ground or single-point ground, provides a single reference point for all ground connections in an electrical system. All equipment and components are connected to this common ground point, typically via a grounding busbar. One advantage of a union ground is that it reduces ground loops and noise by providing a consistent ground reference. It also simplifies troubleshooting by providing a single point of reference for ground connections. An Ericson ground, also known as a distributed ground or multi-point ground, has ground connections made at multiple points throughout the electrical system rather than a single common ground point. Each component or subassembly has its own local ground connection. Advantages of an Ericson ground include reducing ground noise and interference by minimizing the impact of local ground potential differences. It can also improve circuit performance by isolating different parts of the system electrically. The key differences between these grounds are as follows. Firstly, the ground connection for a union ground is a single point, while for an Ericson ground, it's multiple points. Secondly, a union ground has reduced ground noise, but an Ericson ground potentially has higher ground noise. Thirdly, troubleshooting a union ground is simpler, but troubleshooting an Ericson ground is more complex. Fourthly, a union ground is suitable for systems with low ground noise requirements, while an Ericson ground is suitable for systems with high ground noise sensitivity. A union ground is often used in systems where ground noise and interference are critical, such as audio and video equipment, or high-frequency applications. An Ericson ground is used in systems where ground noise is less critical, or where isolating different parts of the system electrically is important, such as medical devices or industrial control systems. In summary, the choice between a union ground and an Ericson ground depends on the specific requirements of the electrical system and the level of ground noise that can be tolerated. Understanding the advantages and disadvantages of each type of ground is crucial for designing a robust and reliable electrical system. Union grounds, providing a single point of reference, excel in minimizing ground loops and simplifying fault finding. Ericson grounds, with their distributed connections, are advantageous when isolating different components and reducing the impact of local ground potential variations. Considering factors such as the sensitivity of equipment, the frequency of operation, and the potential for interference will guide the selection of the most appropriate grounding strategy. Furthermore, adherence to relevant electrical codes and standards, such as those outlined by the NEC or similar regulatory bodies, is essential for ensuring safer and effective grounding practices. The National Electrical Code, or NEC, provides comprehensive guidelines on grounding and bonding requirements for electrical systems. These guidelines cover aspects such as the size and type of grounding conductors, the methods of connecting equipment to ground, and the requirements for grounding electrodes. The NEC also addresses specific requirements for different types of electrical systems and equipment, such as those used in healthcare facilities, industrial plants, and hazardous locations. Compliance with the NEC is crucial for ensuring the safety of personnel and equipment, as well as for preventing electrical fires and other hazards. In addition to the NEC, other industry standards and best practices provide guidance on grounding and bonding techniques. These standards may address specific applications or industries, such as telecommunications, data centers, or renewable energy systems. Following these standards can help to ensure that grounding systems are designed and installed in a manner that meets the specific needs of the application. Effective grounding and bonding practices are essential for ensuring the safe and reliable operation of electrical systems. By understanding the principles of grounding and bonding, and by following relevant codes and standards, electrical engineers and technicians can help to prevent electrical hazards and ensure the integrity of electrical systems. It's important to consider the specific characteristics of the electrical system and the surrounding environment when designing a grounding system. Factors such as soil resistivity, the presence of corrosive substances, and the potential for lightning strikes can all affect the performance of a grounding system. Proper planning and design are essential for ensuring that the grounding system is able to effectively protect personnel and equipment from electrical hazards. Regular inspection and maintenance of grounding systems are also crucial for ensuring their continued effectiveness. Grounding connections should be inspected periodically to ensure that they are tight and free from corrosion. Grounding conductors should be checked for damage or deterioration. Grounding electrodes should be tested to ensure that they are providing adequate grounding resistance. Any deficiencies should be corrected promptly to maintain the integrity of the grounding system. The implementation of proper grounding techniques not only enhances safety but also contributes to the overall efficiency and reliability of electrical systems. A well-designed grounding system minimizes the risk of electrical shock, reduces electromagnetic interference, and protects sensitive electronic equipment from damage caused by voltage surges or transients. Furthermore, effective grounding can improve the performance of electrical equipment by providing a stable reference point for voltage and current. The choice between a union ground and an Ericson ground, therefore, must be carefully evaluated based on the specific requirements of the application. In scenarios where sensitive electronic equipment is employed, a union ground may be the preferred choice due to its ability to minimize ground loot and reduce noise. However, in applications where electrical isolation is critical, an Ericson ground may be more appropriate. The decision-making process should also take into account the potential for future expansion or modification of the electrical system. A well-designed grounding system should be flexible enough to accommodate changes in the system configuration without compromising its effectiveness. This may involve the use of modular grounding components or the provision of additional grounding points to accommodate future equipment additions. Moreover, the selection of grounding materials should be carefully considered to ensure compatibility with the surrounding environment. In corrosive environments, the use of corrosion-resistant materials such as stainless steel or copper-clad steel is essential for preventing premature failure of the grounding system. The proper installation of grounding conductors and electrodes is also critical for achieving effective grounding. Grounding conductors should be installed in a manner that minimizes impedance and ensures a low resistance path to ground. Grounding electrodes should be installed in locations that provide good contact with the earth and are free from obstructions. In addition to the technical aspects of grounding, it is also important to consider the human factors. Electrical workers should be properly trained in grounding and bonding techniques and should be provided with the necessary tools and equipment to perform their work safely. Grounding systems should be clearly labeled and documented to facilitate maintenance and troubleshooting. And safety procedures should be in place to ensure that electrical work is performed in a safe and controlled manner. By addressing both the technical and human aspects of grounding, organizations can create a safer and more reliable electrical environment. This not only protects personnel and equipment from electrical hazards but also contributes to improved productivity and reduced downtime. The principles of grounding are applicable to a wide range of electrical systems, from small residential installations to large industrial complexes. Whether it is a simple lighting circuit or a complex control system, proper grounding is essential for ensuring safety and reliability. The specific grounding requirements may vary depending on the type of system and the application, but the underlying principles remain the same. A thorough understanding of these principles is essential for anyone involved in the design, installation, or maintenance of electrical systems. In recent years, there has been increasing emphasis on the use of grounding techniques to mitigate electromagnetic interference. Electromagnetic interference, or EMI, can disrupt the operation of electronic equipment and can even cause damage. Proper grounding can help to reduce EMI by providing a low impedance path for unwanted currents to flow to ground. This can prevent these currents from interfering with sensitive electronic circuits. There are a variety of grounding techniques that can be used to mitigate EMI. These include the use of shielded cables, the installation of ground planes, and the use of filters. The specific techniques that are used will depend on the nature of the EMI and the characteristics of the electrical system. The development of new grounding technologies is an ongoing process. Researchers are constantly exploring new ways to improve the effectiveness of grounding systems and to reduce the cost of grounding. Some of the areas of research include the development of new grounding materials, the design of new grounding electrodes, and the use of advanced modeling techniques to optimize grounding system performance. The future of grounding is likely to involve the increased use of advanced technologies to improve the safety and reliability of electrical systems. These technologies will include smart grounding systems that can monitor the performance of grounding systems and automatically adjust their parameters to maintain optimal performance. They will also include new grounding materials that are more effective at mitigating EMI. And they will include advanced modeling techniques that can be used to design grounding systems that are tailored to the specific needs of each application. By embracing these new technologies, we can create a safer and more reliable electrical environment for everyone.